Okay, thank you, and thank you for making it back so early after lunch. Really appreciate it, and hope you're enjoying the event today. My presentation is based on how to predict cancellations, hotel cancellations with machine learning. And to that end, I'd like to start off with a question. How many of you have had this experience before? You book a hotel, whether for business or for pleasure, you're very excited about going, and then for whatever reason, you turn around and you cancel your booking. How many of you have done that before? Okay, so quite a lot of us have committed that sin, so to speak, now. What hotels won't tell you, at least not explicitly, is that they really don't like it when we do that. Can anyone tell me why? Exactly. When you book a hotel and then cancel, they are losing cash from the other person who would have booked and committed to that booking but now can't. And as a result, if you go on to websites like booking.com, for example, you'll often see that the prices for non-refundable options are usually lower than the cancellation option because the hotel is pricing in for that risk. Now, what does this have to do with machine learning, you ask? Well, machine learning can provide a platform for allowing us to determine what type of customers are least likely to cancel their booking, and then from that standpoint allow us to determine what customers are going to be the most profitable and then work on the marketing strategies from there. So in terms of what machine learning can do for us, it allows for identification of factors that could lead a customer to cancel. That's the classification side. We can then use time series forecasting to provide insights as to those fluctuations in cancellation frequency, and we're going to be looking at things like ARIMA, LSTM, how we can use those to predict hotel cancellations, and then look at the profiles of customers who cancel versus the customers that don't, and offer businesses the opportunity to rethink their target market. Now, in terms of this particular project, this is research that has originally been conducted by a couple of researchers in Portugal, and what I decided to do was take what data and findings they've come up with and run additional models on this to see can we come up with additional insights on this particular topic. And the notebooks and data sets are available at the MG Codes and Stats GitHub repository. Now, there are three separate components to what we're going to be doing here today, apart from the data manipulation element. Firstly, there is feature selection consideration. We have a large data set, roughly 40,000 variables, 30 or so odd features, but only a select few are actually going to be important in determining what types of features actually influence hotel cancellations. Once we have those features, we then want to classify the potential customers in terms of their cancellation risk. And to do that, we're going to be using several classification models like logistic regression, SVM. We're also going to be using a neural network as well to see do we achieve a higher accuracy from doing that. And then we're going to look at how we can potentially use time series analysis to predict hotel cancellations using ARIMA and LSTM. Now, I'd like to pose a question to you. What do you think off the top of your head is the most important library in a machine learning project, the most important Python library? sklearn? Not in my opinion, no. Sorry? Pandas? Yeah, you're right, Pandas, and as it happens, you've made a friend for life there, so well done. But I'm not referring to our friend here on the right, as adorable as he might be. What I'm talking about is the machine learning library Pandas. And this is the reason I refer to that library. In any machine learning project, 85 to 90% of the work that we're going to be doing is actually data manipulation. In a machine learning project, we tend to emphasize things like TensorFlow, Keras, etc., scikit-learn, and we think about how we can run the models, fine-tune those models, etc. But in reality, 85 to 90% of your time is actually going to be spent on the more boring stuff, data manipulation, and how we can tweak the data to actually get it to do what we want it to do. And in that regard, data manipulation and machine learning ultimately is what facilitates effective analysis. To illustrate this with an example, let's say we have a classification set, and up there you can see things like whether the customer cancelled their booking or not, their lead time, or in other words, the time between when they made the booking and when they actually stayed at the hotel, along with the dates which have been separated into weeks, months, etc. Now, if we want to do a time series analysis, this data set in its current form is going to be no good to us. What we want is a time series, and if you look down at the time series, data set 1 was transformed into data set 2, all through pandas. What I'll do is I'll just navigate to the Jupyter notebook very quickly, and you can get a close-up of what's happening. We have a hotel cancellation data set here. Just bear with me one moment. Yeah. Okay. We have our hotel cancellation data set here. We have cancellations, we have lead time, all of our other features as well as dates. And when we use pandas, we are able to use different data manipulation procedures to ultimately manipulate the data. Firstly, we're using concatenate to join the dates and the cancellations. Then we're aggregating the values in the data frame, and then we're summing them up. And then we have a time series. And that's just one example of how pandas is important and how it helps us achieve that goal. So just to give a more intuitive overview of this, we're merging the year and the week number in that data set that you saw. We're then merging the dates and the cancellation instances, and then we are summing up the weekly cancellations, ordering by date, and this is what allows us to gather a time series. We wouldn't have been able to do this without pandas. Now, in terms of, before we get into the time series, let's look at the classification, classifying potential customers in terms of their cancellation risk, whether they'll cancel or not. Now, as I said before, of all those potential features that we saw in that data set, only a select few are actually going to be of importance in determining whether a customer will cancel or not. And there are many ways we can use feature selection to try and determine that, but what we're going to be using in this instance is the extra trees classifier. And the way the extra trees classifier works is it takes features, runs them relative to the dependent variable or hotel cancellations, and uses it to rank features. The higher the score, the more important the feature in most cases. Now, we can see that we have a ranking of variables and we have the top 6 features, but you shouldn't just trust the numbers in their own right. You should always take a look as to whether they make theoretical sense. For example, things like country of origin. This particular data set was run on a hotel in Portugal, and what we found was that the country of origin, the customers most likely to cancel, were actually from Portugal, because it's a lot easier for somebody based in the country to cancel their reservation than somebody who's based outside the country and is looking to make a commitment to a holiday or a booking. Deposit type, if somebody has put a deposit down, they are less likely to cancel. In terms of lead time, if somebody has a higher lead time between when they make the booking and when they actually decide to go there, then it's more likely that they're going to cancel that booking. But things like reservation status, we see that it has the highest score, number 23, but reservation status in that particular data set means the same thing as whether the customer cancels or not. To take that as a feature in our model would ultimately lead to a lot of overfitting and would be very misleading. Now, when we talk about accuracy, we have our model, we want to do our classification, we talk about accuracy, and we want to get as high accuracy as possible. My motto is always 90% accuracy is great, 100% means you've overlooked something. And oftentimes, I'm sure you've had it happen to you, you'll run a model, you'll get a very high accuracy, and then you're very excited that your model seems to work. But a lot of the time, if you come up with a high accuracy, it means more often than not that you've overlooked something. We have the training accuracy, that is the accuracy of the model in predicting other values in the data set, or the training set rather. We have the validation accuracy, which is a subset of that training set that we're using to validate the results as we go and then adjust the model parameters as we see fit. But then we have the test accuracy, and the test accuracy is completely unseen data, data that we haven't seen before, and that we want to determine whether this model actually works on unseen data, which is ultimately the aim of any machine learning model. Now, in terms of classification, what we're going to be doing on the support vector machines, we have two hotel data sets. Two Portuguese hotel data sets. One, I believe, was in somewhere like the Algarve or something, and another one was in Lisbon. What we're doing is we're building the model on the first data set and we're testing it on the second data set. And what results we actually came up with were that the support vector machines showed a slight increase in accuracy in predicting the cancellation frequency over logistic regression. And again, just to go back to our Jupyter notebook and just to provide some context as to how this works. We're setting up our data manipulation procedures. We're doing our extra trees for feature cancellation. Then we are running the logistic regression based on the features that we deemed important: deposit type, lead time, cancellation. Then we're coming up with the ROC, which is a AUC, which is a standard measure for determining the accuracy of a classification model. And when we come up with the confusion matrix for the two, we're finding that the SVM is slightly better on predicting the test set, and we have an AUC of roughly 74%. Now, an interesting thing is, would a neural network do any better? Well, in this case, we can see that the AUC for the SVM was 74%, but the AUC for the neural network was just under 76%. And this is bearing in mind that we used 500 epochs to actually train that neural network. Now, do you think that's an appropriate use of resources necessarily? I see some shaking heads, so I'll take that as a no. When you run a machine learning model, you always have to take into account the accuracy versus the resources that are needed to achieve that accuracy. If you're spending a lot of money on running your own data center, or you're trying to spend a lot of time building a neural network model, to come up with a couple of more points in accuracy may not be worth it from a logistic standpoint if running a neural network is not going to actually do what you want it to do in terms of gaining a meaningful improvement in that accuracy. Now, underlying that point, it means that more complex models are not always the best models. In other words, we shouldn't necessarily run a neural network just because that is the buzzword, that is what everybody is doing. We want to make sure that we achieve our aim in the most efficient way possible. And if that means running a simpler model to get a similar level of accuracy, then that is something that can work for our use case. That's the classification part. In terms of time series analysis, what would you say is the main difference between those two series, those two orange lines? Would any of you think that the second is more volatile than the first, for example? I would say so. And in that regard, if we have two time series but they have different makeups, then it stands to reason that the models we run on them, one model might perform very well on one series, but then the same model might not perform well on another. And underscoring this point, we can see that on the first time series, which has a trend, the ARIMA model performed better. And then for the second data set, LSTM performed better. And to give you an overview of these models, ARIMA is a tool used in time series that we use to attempt to forecast future values based on their present value. We have P, which is the number of autoregressive terms, D, which is the number of differences to make the series stationary, and then we have Q, which is the moving average terms or the lags of the forecast errors. Now, that's fine when we have trend data and we have data that follows a predictable pattern. But what about when we want to analyze volatile data, or data that's very jumpy in nature? We can use what's called an LSTM model. Now, an LSTM model is a type of neural network, but it is most often used to analyze sequential data. A normal neural network doesn't take into account the fact that there are dependencies from one period to another that a neural network won't necessarily pick up. Now, LSTMs are a type of recurrent neural network, and as a result, they work particularly well with volatile data. Now, in terms of constructing the LSTM model, and again, we'll go to the Jupyter Notebook in a bit and see this, we're taking the cancellation value at time t, which we're predicting by the 5 previous values, or the 5 previous weeks. We're constructing this in terms of weeks. We're then using min-max scaler, scikit-learn, to scale the data between 0 and 1. And then when we configure the neural network, we have our mean squared error as our loss. We're using the Atom optimizer, and we're training it across 20 epochs. And again, this comes back to the whole efficiency argument of making sure that we are only using as much computing power or as much resources as we need to achieve our aim. When I ran this initially, I initially used 150 epochs, but when I used 20 epochs, the accuracy was virtually identical. So using so many more epochs just for prediction purposes is not necessarily the best use of our time. Now, in terms of the LSTM results, and I'm going to be looking at the second data set here, the more volatile data set, we can see on the green line that the LSTM is predicting the direction of the cancellations across that trend, and it's working better with the volatile data. And what I'll do, just to show you how the LSTM model is actually working, this is a separate Jupyter Notebook in itself. We are importing our libraries. We are taking the data, we're formulating the time series of pandas as we said, and then we're forming a data set matrix taking the previous 5 values, and this is done with experimentation. We're taking into account excuse me, we're taking into account the previous 5 values. Running the model across 20 epochs, you can see that we have the input shape. Just go back down. We're plotting the predictions, and then we're coming up with predicted versus actual cancellations per week. We use this prediction across the training and validation data, but then we want to take unseen data. And once we do that, we are coming up with our mean directional accuracy of 80%. It predicts the correct direction 80% of the time. And we're coming up with our root mean squared error as well. And underpinning all of what we've been talking about in terms of model selection, etc., we can actually sum this up by what's called the no free lunch theorem. ARIMA was very good at predicting the first data set, but it wasn't so good at predicting the data set for the second time series, and vice versa for LSTM. Just because a particular model works for problem A, it doesn't necessarily mean that it'll work as well for problem B, and we need to make sure that we're not taking shortcuts by just taking a model that works very well on one time series and then running it across everything. We want to make sure that we are running each model based on the data that suits it. Now, in terms of model selection considerations, this is something that is often called a brute force attack, and it's not something that should be done without really analyzing the data first and understanding it. But one potential solution to determine what models should be run is to run a subset of the data across many models, see which models are performing the best, and then run the full data sets across that model. Now, in terms of data architecture, so we have our machine learning models, we have our analysis, which we're doing very well, but what type of architecture should we be using to implement that? Does anyone have any suggestions? Anyone here use the cloud? Use a cloud solution to run machine learning models? Okay, well, something you might find handy then is Amazon SageMaker. Amazon SageMaker is part of Amazon Web Services, and it works by committing a repository to the notebook and then running that notebook in the cloud. Now, there are several advantages of that. The first one being that it's easier to coordinate Python versions across users. I'm sure you've had an experience where, let's say, you're building a model in Python 3.6, everything runs perfectly, and then you upgrade to 3.7 and that all goes out the window. If you're using a cloud environment, then it's going to be easier to coordinate your model, or your script rather, across different Python versions. It gives you the ability to modify computing resources as you need to run models. You may have a relatively simplistic model that you don't need to use a lot of computing power for, so you can use Amazon SageMaker, but if you have something more extensive that you want to run, you can do that as well. There's no need for upfront investment. You don't need to go out and build your own data center. If you need to run something particularly powerful, you can pay for what you need as you need it. And following on from that, running and maintaining a data center then becomes unnecessary. Now, sample workflow on Amazon SageMaker, and you can try and run this by yourself if you would like. You can add the repository from GitHub or the AWS code commit. Just as an example, the repository that I referred to earlier, MG Codes and Stats, contains these notebooks. And what we do when we commit these notebooks in the repository to Amazon SageMaker, that then becomes part of the SageMaker environment, and we can run these notebooks in the cloud. Just to provide you with some visuals, just for this to make sense. We have the Amazon SageMaker environment. We have the default repository. We're pasting our repository there, giving the address. We're then defining the notebook. We're running the notebook instance type here. We're running a T2 medium, but we could run a T2 large. We could run something that has more computing power. And then we can create our notebook instance, and we can generate the machine learning solution in the cloud. Now, to summarize the findings, when we ran the classification models, we got an AUC of 74%, which means that there's 74% accuracy in predicting hotel cancellations. For the first data set, we see that ARIMA showed a higher mean directional accuracy than LSTM. It showed a higher root mean squared error, so it performed slightly worse on that basis, but it performed better on mean forecast error. So it means that ARIMA is forecasting better than LSTM. However, the opposite is the case for the second data set. LSTM has a much lower root mean squared error and mean forecast error, meaning that the forecasts from LSTM are proving to be a lot more accurate, but ARIMA still works in predicting the mean directional accuracy. And in that regard, to wrap this up, data manipulation is an important part of a machine learning project. There's no free lunch when we run a machine learning model. We always want to make sure that the model is appropriate to the data, and we always want to pay attention to the workflows that are being used and the relative advantages and disadvantages of each. That concludes my presentation. Thank you very much for your time, and happy to take any questions.